This is the basics of a concept that I'm trying to develop on the carbon cycle, which is really cycles. And what I'm trying to do is to make it understandable in terms of its significance as the basis of the science of global climate change and ocean acidification. The big theme here, which I'm working on into again, is that carbon dioxide is forever. Carbon dioxide emissions in the atmosphere last practically forever. And the reason why this is totally definite is because of the carbon cycles. So I've got the carbon cycles divided into four here: land or terrestrial carbon cycle and ocean carbon cycles. And then they divide into a fast carbon cycle, both land and ocean, and a slow carbon cycle, both land and ocean. So the fast carbon cycle is also called the short term, as well as it's biological. I call it a carbon recycle. Its time frame is less than a day to hundreds of years. So, and that is the key importance, so I put it over here again, less than a day to hundreds of years. The slow carbon cycle is also called the long-term carbon cycle. I call them the ultra-long-term and ultra-slow, and that's the carbon cycle. I also call it the carbon sinking cycle. The time frame here is thousands to millions of years. So thousands to millions of years for the slow carbon cycle. Now the land carbon cycle ends up with coal. The ocean carbon cycle ends up with oil and gas, and also limestone. The scientific conclusion, or what the carbon cycle science leads to, is the scientific fact on climate change and ocean acidification that global climate change, temperature increase, and ocean acidification can only stop increasing if industrial carbon dioxide emissions stop. So that is the absolute baseline key for mitigation, for dealing with global climate change, and indeed surviving global climate change. You'll see that the ocean, in both the fast carbon cycle and the slow carbon cycle, the illustration is larger than the land equivalents, and that's because they are larger. The ocean carbon cycle holds a lot more carbon than the land does, and it moves a lot more carbon than the land does. We're starting off with the fast or short-term carbon cycle, which is the biological carbon cycle, and that's because it relies on photosynthesis by green plants, of course. Carbon dioxide here I've illustrated in red. So these red arrows are carbon dioxide. The usual illustration of a molecule of carbon dioxide is one atom of carbon and two atoms of oxygen there. The ocean carbon cycle, the short term, is considerably larger than the land short-term carbon cycle, and we have phytoplankton in the middle of the ocean carbon cycle. Here is the sun and solar energy. My other reason for developing this is for education of younger people, because our younger people tragically are now going to grow up in a world seriously altered by global climate change. And so for the world that they're going to grow up in, they really have to understand atmospheric greenhouse gas pollution in totality, and they really have to understand the realities of carbon dioxide in particular. So there are two land carbon cycles and there are two ocean carbon cycles. They are termed short and long carbon cycles, or the better term is fast and slow carbon cycles. That's the better term with respect to understanding their significance in global climate change and ocean acidification. The short-term fast carbon cycle is a biological carbon cycle, whereas the long-term carbon cycle is a geological one. The short-term I call a recycle, because that's what it does. The short-term carbon cycle does not remove carbon dioxide from the atmosphere for any kind of permanent sense. That can only be done by the long-term or slow carbon cycle. So the time scale is what matters here. The fast, short biological carbon cycle has a time frame of less than a day to hundreds of years. Some trees will last for 1,000 years. That's the limit. On the other hand, the slow carbon cycle operates over a period of thousands to millions of years. So I put this little tiny illustration to take the place of the slow carbon cycles to show that the time frame is so minusculely small compared to the fast carbon cycle. And that applies to both the carbon cycle on land and the carbon cycles that is in the ocean. Both carbon cycles operate, the short-term carbon cycles both operate by way of the photosynthesis of green plants. The short-term fast land carbon cycle is the one that we generally think of when we think of the carbon cycle. And so most people will be fairly familiar with the fact that green plants, grasses and trees, they can take up, absorb carbon dioxide, and with energy from the sun, they are able to do the photosynthesis process by which they incorporate carbon into their growth and their essential processes. All life, of course, is carbon-based. At the same time, as we know, they release oxygen. Now, they take in carbon dioxide and they release oxygen, that's well known. They also, when they decay and die, they also release carbon dioxide. So over varying period of time, whether it's grass or a big tree forest, over varying periods of time, the carbon dioxide which is absorbed from the air is released back to the air. This is, in effect, a closed system. And it's a closed system because of the huge differences, incomparable differences, in the time scale of the fast carbon cycle, which we're talking about now, and the slow carbon cycle. The ocean carbon cycle operates on the same basis of photosynthesis. In this case, the photosynthesis is performed by microscopic green plants called phytoplankton that live on the surface and just below the surface of the ocean. And they, in the same way as our plants on land, they absorb carbon dioxide with the energy of the sun. They do the photosynthesis process, and they take in carbon for their growth and metabolism and life processes. And they also emit oxygen. Similarly, as the phytoplankton decay and die, they will release carbon dioxide back to the atmosphere. So again, because of the incomparable time frames involved, this is a closed cycle. In both cases, the fast and the slow carbon cycle, the ocean is by far the biggest player. The ocean moves by far the most carbon compared to the land carbon cycles. Now we're also looking at the slow carbon cycles, the ultra long-term geological carbon cycle, which is the cycle that can sink carbon, and it operates over millions of years. Again, the ocean carbon cycle is the big player, by far the biggest player compared to the land carbon cycle. Now, also, most of us will know about the land ultra-slow carbon cycle because I think we know that coal takes millions of years to form. Indeed, it does. Coal is fossil carbon, and the other two forms of fossil carbon that are being burned for energy, of course, are gas and oil. These fossil carbons formed mainly in the Carboniferous period. That's why this period is called Carboniferous. And the Carboniferous period was 300 million years ago. So we're now talking hundreds of millions of years. Now, this little tiny spot, it would be an invisible speck if it was done in a realistic proportion. So then we expand this spec up to this long carbon cycle here so that we can follow it. The carbon, this tiniest leak from the forests and the trees and plants in soil gets buried. So we start with burial of this carbon, then pressure. It falls lower and lower and lower into the soil as the soil builds up over time, of course. Pressure and heat and ages of time forms the fossil carbon. First of all, peat is formed and then coal is formed. Peat is still burnt for heat in some regions of the world. So now we pass on to the slow, ultra-slow ocean carbon cycle. And the same thing as happened in the soil happens in the sediment of the oceans. And again, we're talking millions and millions and millions of years. Now, we all know that gas and oil are fossil carbon, that they started to be formed hundreds of millions of years ago, what we're burning, what industrial civilization is burning for energy. And the origin of this carbon is the phytoplankton. In the Carboniferous period, the continents were very much closer together. The ocean, of course, was still vast, and the continents, the land was very wet and watery. It was very much a swampy environment, and so there was a great amount of Earth's surface for phytoplankton and algae to grow. So there was a tremendous amount of, well, there's still a tremendous amount of phytoplankton. It's still a massive amount of biological life on the planet. So all of this, and over many millions of years, formed the gas and oil. So it's phytoplankton that is the originator of the gas and oil that industrial civilization is burning for energy. Sediment burial, pressure, heat, time, fossil carbon, similar to coal. Now there's another form of fossil carbon that is formed by the ocean ultra-long-term cycle, and that's rock, that's limestone, which is calcium carbonate. So the carbon in the carbonate. And best way to think about this is, of course, the White Cliffs of Dover. So there's vast amounts of limestone, of course, all around the Earth. And the White Cliffs of Dover were formed many millions of years ago in the ocean and the ocean sediment. And as the continents have moved, migrated, we have these on our continents and on our land. How that is formed is essentially through what we know of as the food chain in the ocean. That's called a biological pump. It starts with phytoplankton. Phytoplankton are ingested by zooplankton, and then bigger creatures and bigger creatures and bigger creatures, and so it goes, and we end up with the whales. Interesting, the whales that live on plankton. Now, some of the zooplankton that ingest the phytoplankton are shell-making microscopic organisms. And this starts, and their shells are calcium carbonate. So this forms a chain of bigger and bigger and bigger creatures which are shell makers, but it forms a huge amount of these microscopic shell-making calcium carbonate surrounded microscopic animals. And there's a little picture here of a zooplankton which looks like a little snail, and then here is what we're familiar with, which is the seashells. Again, both are calcium carbonate. The disintegrated phytoplankton, zooplankton, sink down and form masses like this, and they form what is called a snow in the ocean, snowing down from the shallow surfaces down to the depths of the ocean. Most of it, of course, is recirculated in the food chain, but a minuscule tiny amount of it gets embedded deep into the ocean sediment, and that's I've represented here with a mass of broken up shells. And so this calcium carbonate containing sediment, pressure, heat, and ages and ages and ages of time forms fossil carbon, which is limestone. The other form is dolomite. Just a note here to say that in the ultra-long-term carbon cycle, eventually over many, many, many millions of years, this carbon will be returned to the atmosphere, so it can be part of the fast carbon cycle again. What we need to know from the point of view of climate change and ocean acidification is how carbon is converted, is to know how carbon dioxide gets to be fossil carbon, how carbon dioxide gets to be coal, gas, oil, and limestone. Now, we are burning up these three kinds of fossil carbon for energy in industrial civilization. We're also burning up the limestone, which is the other form of fossil carbon. And industrial civilization does this to make concrete. And this was discovered by the Romans, how to make concrete. Now, this side of the sinking of fossil carbon, the land side of it, is not operated it's not operating for us anymore. And that's simply because industrial civilization has reversed this long-term carbon cycle and is burning up all the coal at an extremely rapid rate. This is being returned to the atmosphere as carbon dioxide in an ultra-fast rate, which of course has never ever happened on the planet before, nor has anything like it happened on the planet before in the time frame that industrial civilization is doing it. So we only have the ultra-long-term ocean carbon cycle that can remove carbon dioxide from the atmosphere. There is now no other way. Now, there is research and there are papers, etc., being written about a theoretical idea of being able to artificially remove carbon dioxide from the atmosphere. Yes, we can take in more carbon by growing more and more forests, but eventually that carbon will be returned to the atmosphere as carbon dioxide, and so that's only a very, very short term sort of band-aid approach, essential though it is right now, to the problem of climate change and ocean acidification. There is no feasible way of removing carbon dioxide from the atmosphere at any kind of scale, nor of sequestering it so that it doesn't seep back into the atmosphere as carbon dioxide into the atmosphere again, nor of doing it for any length of time. And there is no, at the moment, there is nothing which suggests that that is going to be possible in the foreseeable future. So we really do need to understand that this is the only process that can remove carbon dioxide from the atmosphere. There are other things that we're going to have to do. Conserving biomass, that's essential. Biochar is also excellent. Biochar is also an excellent method of storing carbon for a long time. That's hundreds of years. We can also, of course, manufacture buildings with wood, and thereby making sure our buildings last for hundreds of years of wood, like indeed they have been in the past, and that will sink carbon and buy time with respect to climate change and ocean acidification for hundreds of years. Here is a professional illustration of the all-important ocean carbon pump. This is actually taken from a recent research paper on the ocean carbon cycle. So here we have carbon dioxide dissolving into the surface water, and then it diffuses out of the surface water here. Here are the phytoplankton, the microscopic plants that live on and just below the surface of the ocean water. And here are the zooplankton, the microscopic animals. Now, zooplankton graze on the phytoplankton. They eat the phytoplankton. That's how they grow and develop. And here you see the result of the phytoplankton and the zooplankton disintegrating, the ones that fall through the surface ocean to the deeper ocean, and together they form particulate organic carbon. So you can see why the scientists call this a snow of particulates. And then eventually, with temperature and pressure and ages and ages and ages of time, organic carbon is buried in the seafloor. There's the ocean sediment, eventually gets to the seafloor, and hence we get gas and oil from the phytoplankton and limestone from the creatures, the marine creatures that make shells, those shells being calcium carbonate. Here is a particularly good illustration. It's actually from the IPCC 2014 Fifth Assessment, and part of the section that explains the essential vital importance of the ocean carbon pump in sinking carbon. I'm not going to go through this. Everything's labeled very well. Just leave it for people to look over it in some more detail. So, the fact that it takes millions of years for the ocean to remove, in any permanent sense, carbon dioxide means that this here is a closed system, and the only way to stop atmospheric carbon dioxide increasing is for industrial civilization to stop adding any more carbon dioxide. And that is the absolute definite science of so-called zero carbon emissions. The IPCC 2014 Fifth Assessment stated emphatically in a headline statement that atmospheric temperature and climate, the same applies to ocean acidification, obviously, which they didn't mention. Temperature and climate can only be stabilized if emissions of carbon dioxide drop to, quote, near zero, unquote. So I'd hope that that this concept, if it works, can be actually made a lot simpler by very simple diagrams and text to explain, and that's commonly done with simple animation nowadays. But this more complex, so I've tried to make sure I included everything, and this more complex illustration is also, of course, suits animation.